Okay, let's go ahead and take a look at today's lecture. And today we'll introduce gradient descent as an optimization algorithm. Some of you took 102A with me, and in that class we covered coordinate descent as a method for finding the local minimum, or I guess local maximum of a function. That was coordinate descent, and that was covered in 102A. If you didn't take 102A with me, maybe you didn't cover coordinate descent, that's okay. It's not necessary for learning gradient descent. It's just both of those things, coordinate descent, gradient descent, are both just different kind of algorithms or methods that can be used to find the optimum, or that is a minimum value for a function. So we are using the loss function, which is the mean squared error. We're using that as our objective function. We're saying this is the function that we want to minimize. We want to find the set of parameters or weights that will minimize the mean squared error. So when we are doing linear regression, we want to find the slope and intercept that will minimize your mean squared error, your sum of squared residuals, whatnot. So far what we've been doing is we've been using calculus, okay? We would calculate the derivative, we set the derivative equal to 0, and we solve. And that is kind of the calculus method for finding basically a local minimum or local maximum of a function, and it's been working out for us, okay? And we can do it in matrix notation, which is what we did last week, which is what you're doing in your homework. You take the gradient of the function with respect to your weight vector w, you set it equal to 0, and that's going to help you find the local minimum. And that works when your function is simple, okay? But a lot of times the loss function can get pretty complicated, and you might even be able to figure out the derivative, all right? You might be able to figure out the gradient of your loss function, okay? But setting it equal to 0 and then solving could become this intractable situation, all right? And so in situations like that, we can use computational methods, and the computational methods will help us arrive at the local minimum. So that part where we said, okay, we'll set it equal to 0 and solve, that was easy for the examples we've seen so far. But in the future, that part, okay, here's your gradient, we'll set it equal to 0 and solve, that part can actually get really, really tough, okay? So again, just to step back, our goal is to figure out the set of parameter estimates. For simple linear regression, we're just trying to figure out the slope and the intercept. As things get more complicated, we might have slope in several, we might have several slope or weights associated. You might have several predictor variables, and you might need to figure out the associated weights with each of those predictor variables. Eventually we'll look at neural networks, and in neural networks, you have a whole bunch of nodes and connections between these nodes, and each of those connections have a weight, okay? And if your network gets really big, you might have hundreds of weights to calculate, okay? The key thing to remember is that in all of this stuff, we treat the data as fixed, okay? So there is some data generating process that produces our data, but once we have the data, as far as fitting the model goes, we treat the data as fixed. The loss function that we are looking at, that we're saying we want to optimize, that is a function of just the parameters that we're trying to estimate. So right now, we're just trying to estimate the slope, and we're just trying to estimate the intercept, okay? And so that's what we're going to do, okay? Now, when we're dealing with univariate calculus, when we're dealing with just one variable, the derivative represents kind of the slope of the tangent line of the function, right? You have a function, you pick a point, and the derivative at that point represents the slope of the tangent function. Now, when we have a function of multiple variables, so just now imagine you have two inputs going in, so now our function is kind of the surface The gradient, all right, which is kind of the multivariate equivalent of the derivative, the gradient is now a vector that points in the direction of greatest increase, okay, of the function. So now you have this kind of you have two inputs coming in, you have this surface, you're picking a location, a coordinate, x1 and x2, this is your location x, and the gradient now represents kind of the vector that points in the direction of greatest increase. And so the idea behind gradient descent is that you say, okay, if we're at some location, if this way is uphill, then we're going to move in the opposite direction, okay? And so that way is uphill, then the opposite direction has to be downhill. And so what we'll do is we take a step downhill. That brings us to a new location. At our new location, we calculate the gradient, which says, okay, uphill is this way, and so we'll take a step downhill. So it's kind of like, if you are sitting, if you're in some kind of, wilderness or something, and you're on a hill, and you want to say, I want to get to the bottom, right? Basically, the local minimum would be like the bottom of a valley or something. It's kind of just like your plan. How do you get to the bottom is figure out which way is uphill and go in the opposite direction, okay? And if you keep going opposite of uphill, you're going downhill, and eventually you'll get to the bottom. That's kind of that's the premise of gradient descent. It's a very simple idea, and it's simple to execute and simple to carry out, okay? And we just kind of repeat this iteratively, and eventually we should reach the bottom of the hill, okay? So the gradient descent algorithm, the way it looks, it's very simple. It's one line, okay? This is it, okay? We have some function f, and the input of our function is basically our vector of weights. So right now, our function is the loss function, and our input is a vector of slope and intercept. And so we're going to say currently, we are currently located at some location, w at time n. So we say, okay, right now my slope estimate is 1 and my intercept estimate is 0. Okay, so that's just, some line, okay? Intercept 0, slope of 1. And we're going to say, okay, what I want to do is I want to update what my slope and intercept should be. So at the next iteration at time n plus 1, what slope and intercept should I use? Well, what we do is we take our current slope and intercept, and I subtract off gamma times the gradient of the function at that location. So nabla f is the gradient of the function, the gradient of the loss function at this current location. So basically just take your current location and subtract off, or basically move a step opposite of the gradient. So the gradient points uphill, and we move a step in the opposite direction. Okay, and so you just current location, gradient at the current location, just subtract off a constant times your current gradient at the current location. That's going to give you the gradient at the next iteration. And that's it. That's the entirety of the gradient descent algorithm. It's just this one line. Current location minus gamma times gradient of the current location is your next location. So let's try this out with a simple function. So this is not the loss function. This is not weights, slope, and intercept. This is just some arbitrary 2D function. We've got an x1 and an x2, and I'm just going to demonstrate how gradient descent would work for this arbitrary function. All right, before I do that, let me give you your first view quiz answer for, what is this, week 2 Monday. First view quiz answer is the letter B. B as in bear. B is your first view quiz answer. Okay, so again, this is just an arbitrary 2D function. It's not least squares regression. It's not slope and intercept. It's just x1 and x2. And so I got x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. And so what I'm going to do is I'm going to kind of use this definition of the gradient, which is going to be, it is a vector of partial derivatives. So we've got the partial derivative of f with respect to x1, and the partial derivative of f with respect to x2. So if you take the partial derivative of this thing with respect to x1, you get 2x1 minus 2 minus 0.5 x2, and that zeroes out. Okay, partial derivative of this thing with respect to x2, that's 0, we get negative 0.5 x1 plus 5 x2. So this is a vector with two elements in it. The first element is this, and the second element is this. This is a contour plot of this function over here, x1 squared minus 2x1. So basically we have this bowl, okay, I guess a paraboloid. So you kind of, I don't know if you can visualize this thing, but you basically have, you know, kind of like this big bowl here. And what we're trying to do is we're trying to find the minimum, which on this contour plot is right here, right? Are we okay with this contour plot? It's just kind of like you've got this ellipsoid paraboloid thing. Okay, not ellipsoid, but this paraboloid thing, and you know, we're taking basically like slices of it, and when you slice each thing, you get ellipses, you get these concentric ellipses here, okay? And this is kind of what we're looking for, and we're just kind of looking for, you know, the location here. So I'm going to just start at some arbitrary location. We're going to start off at x1 is -5 and x2 is 4. This is just some arbitrary location. So this is x1 and x2 at time 0. And I'm going to say, okay, what is the gradient at this location? So using kind of just our partial derivatives, we said the partial derivative of the function with respect to x1 is this, okay? And so I'll just plug in our current values. Our current values, I plug in -5 and 4, and I get 2 times -5 minus 2 minus 0.5 times 4, and that multiplies out to that adds up to -14. Okay, for the second element, which is -0.5 x1 plus 5 x2, I plug in our current values, okay, of -0.5 and 4, and my value here ends up being 22.5. Okay, so that is the gradient, and that would be the arrow that points to the steepest ascent here. So if I come, it's kind of hard to see. I think -5,4 is this top left corner, okay, up here. And then basically we're saying if we wanted to go in the direction of steepest ascent, I would go use the vector, you know, -14 and then up 22.5. And so we're going kind of in a direction starting here and going into, you know, kind of towards the, I don't know, the O or the U or something, right, in this kind of direction. That's how you would get uphill. And what we want to do is we want to go in the opposite direction. So I'm going to just use an arbitrary gamma, step size of 0.1. And so I'm going to do current location, -5, 4 minus 0.1 times the gradient, okay? And so we said, what is the gradient? The gradient is -14, 22.5. Multiply that by 0.1, and -0.1. And so now I get plus 1.4 minus 2.25. And so -5 plus 1.4 is -3.6. And 4 minus 2.25 is 1.75. And that's what we get, okay? In R, I can compute it like this. I can say, here's my function, x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. And then the gradient is a function of x1 and x2, and it's going to return basically a vector of partial derivatives. And so the first partial derivative, df with respect to df dx1 is going to be this, and df dx2 is this. So that's it returns a vector of, you know, vector of partial derivatives here. Okay. And so if I say we're going to start at -5, 4, I can calculate the gradient at this location of -5, 4, and then the endpoint is going to be start minus gamma of 0.1 times the gradient of this, and it says I get -3.6, 1.75, which is exactly what I got when I calculated by hand. And so I can plot this, and so here's my starting location, -5, 4, and if I say we're going to end at -3.6, 1.75, the ending location is here. So if we start here and we say uphill is in this direction, we're going to go downhill, we're going to go in the opposite direction, and we end up right here. And then we repeat the process, it's iterative, so now my starting location is -3.6, 1.75, I'm starting here, and we're going to say, okay, what is the direction uphill? And we calculate the gradient, all right, the gradient there is -10.075, 10.55, and we say, okay, what we will do now is we will move in the opposite direction, start minus gamma times the gradient, and it says, okay, after that, our next coordinates are -2.59, 0.695. And so at the next iteration, we move over here, okay? So we're going, our direction changes a little bit, and then here's our location, and we can kind of repeat this over and over. So I've just created a loop, all right? And so my loop, again, this is, it's really just one line here, okay? And I just have one line, another line to store basically what my x vector is, okay? So I start off here, and then, I'm going to store my responses and locations. So I'm going to store it in x vector, and then I just update, and this is the gradient descent. Take your current x vector, subtract off gamma times the gradient of your current x vector, and we run through that, and we just kind of keep calculating new locations, and we're storing those locations. And this line is just to kind of plot all of those locations that I've plotted. And so I just have a for loop, and at each iteration we're going to plot an arrow where the start location is here, and then the end location is at the next line. So start location is on line I, coordinate 1, coordinate 2, and then the ending location for the arrow is line I plus 1, coordinate 2. And if we do that, this is the resulting plot here. Okay, so I think these first two iterations are what we have here. Okay, starting here, and the second iteration goes there, and that's what we have there, right? Okay, and then here is just kind of the continuation, iteration 3, 4, 5, 6, 7, 8, 9, 10, and it keeps going, and we can see it's getting us towards basically, what we can perceive to be the minimum. Okay. One thing to note is that our steps do get smaller and smaller and smaller and smaller, and that's one thing about gradient descent is it's kind of like the next step you take is related to how steep it is, and so as you get closer to the minimum, if it's a smooth function, then the slope gets shallower and shallower and shallower. So it's kind of like, it's like a Zeno's paradox type of thing, where it's like at every iteration you go you get halfway closer and halfway closer, and so you'll after 1,000 iterations, you're like a billionth of a way, but you're never actually at the end. Okay, but you're gonna hit the limits of kind of your machine to epsilon anyway at that point. But you can see that the steps just keep getting smaller and smaller and smaller because it gets flatter and flatter and flatter. So what is the gradient as you're getting close to the very bottom? The gradient is this very small, shallow slope, and it's pointing, saying this is uphill, and you can still go downhill, but it's really, really small at that point. Okay, but that's what we see. So this is the result of gradient descent here. Okay. Now I could choose a different gamma. So here my gamma was 0.1. Okay, so every time I take a step, I'm doing start minus gamma times the gradient. Okay, I could shrink my gamma. Okay, and I can say gamma of 0.03. And you can see each of my steps now are even smaller, okay? So rather than taking a big step downhill, we're taking just a tiny little step downhill. And that will still get us towards towards the bottom, it's just all of my steps are really, really tiny, so it'll take a lot of iterations to get to the bottom. So, computationally more expensive because you now have to take a whole bunch of iterations to get downhill, okay? Here's a bigger one. I'm taking gamma of 0.15, so I'm taking a big step, and we can see, we get towards the center faster, okay? You can run into problems, though, where if you take a gamma that is too big, okay, we're supposed to take a step downhill, and we're saying downhill is in this direction, okay, except you've taken such a big leap in that direction that you actually go past the bottom and you end up on kind of like, if you're imagining like a hill or a valley, okay, and you're starting over here and you say, okay, downhill is in that direction, and normally you take steps downhill, but now we're taking, our gamma is so big, we're taking like a leap, and we take a leap in that direction and we end up on the other side of the valley, okay? We've gone past the bottom and we ended up on this side of the valley, okay? And so now we say, oh, which way is downhill? Now we're like pointing in a completely opposite direction. And then we take a leap, and we take such a big leap that we end up on the other side of the valley. So you end up with this kind of this zigzag pattern because you're taking such big leaps, okay? And actually, if you pick a gamma that's too big, okay? So remember, your gradient is related to how steep the slope is, okay? And so right now, our bowl is at the bottom, the slopes are shallow, and as you get farther away, the slopes, the sides of the bowl get even steeper and steeper and steeper, okay? And if your gamma is too big, now you're taking leaps to the other side of the valley, on the other side, and your leap was so big that you actually end up higher with an even higher slope, okay? And so now your gradient is even bigger than, so normally what we would expect is you take a step downhill and you end up in a place with a shallower slope, so your next step is smaller and your next step is smaller and your next step is smaller. That's what we kind of expect. But over here, we've taken such a big step that we end up on the opposite side, and not only on the opposite side, but we end up in a location where the slope is even steeper. So when we calculate the gradient, it says, oh, you need to take an even bigger step in the opposite direction. And so now you're like bouncing back and forth, and it diverges, because now you're like, I don't know, you're going to end up climbing up the sides of the sides of the valley there. Okay, so steps that are too big can overshoot and then fail to converge. So these are just some issues with gradient descent. Is a lot of times it works, and it's a kind of a handy algorithm that we like to use a lot, but there's no guarantee that it will converge, and you don't really know what gamma you should use. All right, you can't just look at a function and say, well, with this function, I know that the gamma I should use is 0.1, or I know the gamma I should use is 0.15 or 0.01. You really don't know, okay? So there's a lot of kind of trial and error aspect to figuring out what is the right gamma. So in some cases, the gamma you want to use is like 5, okay? But here, a gamma of 0.5 is too big that it's not going to converge, okay? Gamma of 0.3 will converge, but it's not going to be the most efficient. Gamma of 0.15 is pretty good and will get us there quickly. A gamma of 0.03 will get us there slowly, okay? But yeah, a gamma of 0.5 is now too big and it will overshoot. But there might be situations where you need to use a gamma of 1 or even 10 or something, depending on the function. And there's not really a way for you to just look at a function and say, oh yeah, I know exactly what gamma to use, okay? So choosing gamma, we also call this the learning rate, can feel quite arbitrary. There is a lot of trial and error. Your general recommendation is start with a small number like 0.01, and then see if it kind of you can kind of see the value of the loss function. If it seems like it's moving correctly, then you can try increasing it, bumping it up, and seeing if there's a point where you reach issues of instability. Okay, there have been advances and research in this field to help us try to figure out a learning rate. So an algorithm called ADAM is like adaptive something. I don't know what it stands for. I don't remember, but it's basically it adjusts the learning rate as the algorithm is running as part of the decision-making process. So again, we're just kind of sticking with the simple one-line algorithm of just saying, where did it go? Take your next step, just current location minus the gradient at this is going to be your next location, right? And you can make it more complicated and things like that. We're not going to worry about it, but that is something that exists. So right now we're just going to leave it and just use some guess and check. Okay. All right. So let's go ahead and apply gradient descent to this familiar problem of ordinary least squares regression. Okay. So in ordinary least squares regression, the loss function, the function that we are trying to minimize, our objective function, is the mean squared errors, okay, or mean squared residuals. And in matrix notation, it is our target values minus x times our weight matrix, right? So we do t minus xw transpose t minus xw, and then we multiply that by 1 over n, and that will give us the value that is equivalent to the sum of squared residuals. So we want to minimize this, and so we're going to say, what is our gradient? All right, and we can do this analytically using the partial derivative with respect to w0. And so if I expand this out in non-matrix notation, this would be the partial derivative with respect to w0. This is the partial derivative with respect to w1. But rather than using kind of the partial derivatives, I'm going to go ahead and use the matrix notation, the vector-based calculus, and we did this last week, and you have to do something very similar in your homework, right? In your homework, you just have the matrix A in the middle of all of this stuff, but your results also end up being quite similar. And so anyway, last week we went through the steps, and we said, okay, the gradient of the loss function with respect to W is this. And what we did last week was we said, okay, to figure out W, we're going to set the gradient to equal to 0. That's where that's where there's going to be a local minimum, and we're going to set that equal to 0 and solve for W. Okay, but we're going to pretend that we don't know how to do that. Okay, that we don't know how to like multiply by the x transpose x inverse or something like that. So we're going to say, okay, here's my gradient with respect to W, but I don't know what to do next. Okay, I want to find the local minimum. I don't know how to set this thing equal to 0 and solve. Okay, because that's basically what, in the future when we're doing like neural networks, we'll be able to figure out the gradient, but we're not going to be able to set it equal to 0 and solve. So how can we figure out the values of W that will minimize this function? We basically want to find where this thing is equal to 0, but how do we do that? We're going to use gradient descent. Okay, so we have the formula for the gradient. Okay, so what we're going to do is we're going to say, okay, let's just start off in an arbitrary location. In our case, our arbitrary location is some arbitrary intercept, arbitrary slope. And then we're going to say, okay, find the gradient at this location. And we can find the gradient because we have the formula for the gradient. Okay, and we're just going to take our current location, subtract off gamma times our gradient. So to illustrate this, I have a fake data set of 3 data points, okay? And this is just to keep everything very simple. So my x values are 1, 3, and 5, and the actual values corresponding to this are 4.8, 11.3, and 17.2, okay? And I'm going to go ahead and cheat and give you the answers. So if you were to fit ordinary least squares regression to this data, it will say your intercept is 1.8 and your slope is 3.1. Okay, and so you can see if I plug in 1.8, and 3.1, our first value would be like 4.9, And then if I do 3 times 3.1, what would I get? I would get 9.3 plus 1.8, and I would get 11.2 or something. So I would get, some pretty close values here. But this is what the answer would end up being. And if I plot this, these are our 3 data points, 1, 1.8, or 1, 4.8, 3, 11.3, and 5, 17.2, and our fitted line looks like this. So this is the answer. And that's just using LM. Okay, but we're pretending like we don't know how to get to this solution. What we have is we have the loss function, we have the gradient of the loss function, and we're going to use gradient descent to figure this out. Okay, so here's my gradient. All right, and this value 2 over n is just it's just a constant. Okay, and so remember, so here I've got w minus gamma times this, and I can just say, all right, let gamma or lambda or whatever, some constant equal this thing times 2 over n. So I'm going to say I want a function that's going to calculate the gradient for our current value of w. And so this is going to be x transpose, negative x transpose times t plus x transpose times x times w. And so this is going to calculate the gradient of the function here. Okay, and so here I just start off with an arbitrary value, arbitrary of intercept of -1 and a slope of 1.5. That is not going to be the correct answer, okay? Because the correct answer is intercept should be 1.8 and the slope should be 3.1, okay? So here I'm just picking an arbitrary intercept and an arbitrary slope. I'm using a small gamma of 0.02, and I say take 1,000 iterations, run gradient descent. So all we do is we take our current location, our w vector, which currently starts off at -1, 1.5, and I'm going to subtract off gamma 0.02 times calculate the gradient at our current location w. Okay, and I want you to see that the code is a direct translation of the math and the algorithm, right? Sometimes I think students are intimidated by the idea of, okay, here's the math, now turn it into code. But it's not that hard, okay? It's because you can see this is a direct translation, right? I'm just saying, okay, what is my current value of w? It's w vector minus gamma times the gradient at w, which is minus gamma times the gradient at this. And then the gradient is this function that we wrote right here. Okay, what is the gradient? It's just x transpose times t plus x transpose times x times w. So we're just doing direct translations from the math to code here. And so I run 1,000 iterations of this. And after 1,000 iterations, it says the value I got for the intercept is 1.799995, and the value for my slope is 3.100001, okay? Which is pretty close to the true answer of 1.8 and 3.1, okay? So it's pretty close. It's not exactly that. If I ran it for like another 10,000 iterations, I'd probably get even closer. But again, we're running, we're that issue where it's like you take a half step closer and a half step closer and a half step closer, but every single time your steps get a little bit smaller, so you never actually reach the destination perfectly, okay? But you get really, really, really close. And so, I could probably bump up my gamma a little bit. I could probably run for a few more iterations, but this is getting us pretty close to the final answer. Right? And that's something you have to be comfortable with when you're doing computational statistics versus math. In math, you come down to exact answers. When you're doing computational stuff on your computer, you're not going to get exact answers. You're going to get estimates that are pretty good. And the fact that you are using a computer, you're kind of like acknowledging that, because the computer isn't even able to do real numbers, right? The computer is only able to do approximations of real numbers in floating point form, which is pretty good in most circumstances, but it's not exact. So that is something that we have to kind of accept and say, all right, I'm getting something pretty close. It's not exact, and that's where we are. Okay, so what I want to show on these next few slides is kind of like what is happening with when we do gradient descent here. Okay, so this is just code to get all of this plotted up, but basically this is the contour. The contour showing what is the loss function. Okay, what is the mean squared error or the sum of squared residuals? One of those things. Okay, for different values of the slope and different values of the intercept. And we can see the minimum is right here at the center of this ellipse, and that corresponds to an intercept. If I could kind of draw the line, so for those of you watching the video, I'm doing something on in class here, but so this location here is kind of the minimum, and that corresponds to like the intercept of 1.8, and the slope, I think, should be 3.1. So if I go across 3.1, it should be, I don't know, it's really hard to get the line. I don't know, is that right? 3.1? It's hard to do this up close, but it should be. It should be the location of the center of this ellipse down here, where we can visually say, all right, this is where the minimum is, should be at that location 1.8, 3.1. Okay, 1.8 for the intercept, 3.1 for the slope. And this red line traces the path that gradient descent took. Okay, so this is like this weird shaped paraboloid where the sides are really steep, and this side, the bowl is kind of wide. It's kind of like this, this very weird shaped bowl. Okay, thin and long bowl. Okay, so just imagine like I don't know, you've squeezed some plastic mixing bowl or something like that. Okay, and this is the path that we took. So we started off at the location, intercept is -1, slope is 1.5. So that was my starting location here. I started off at this arbitrary location of intercept is -1 and slope is 1.5. Okay, and so this is what the plot looks like. So when the intercept is -1 and the slope is 1.5, okay, this is what our line looks like. Okay, so the true values were like 1, 4.8, and 5, 11.3, and I forget what this, or 3, 11.3, and 5, 18 point something. So this is the data, and we want our red line to fit closely to the data. And right now our red line is doing a terrible job. This is our estimated line where the slope is 1.5 and our intercept is -1. It's doing a terrible job. Okay, and so this is where we start. And so we say, okay, use gradient descent. At the next iteration, it says take a step, and now your intercept is -0.772 and the slope is 2.3. So our line got steeper. Okay, the slope is 2.3. And our intercept is higher, and we can see, okay, between this line and this line, the second line does a better job than the first line. All right, so our squared residuals are a little bit smaller, and this is where we are in the contour. Okay, we take a few more iterations. Okay, so after 5 iterations, we are here. Our intercept is -0.45, and our slope is 3.3. Okay, and we say, okay, well, this is an improvement, right? So we used to be here, and now our line looks like this. And we can say, okay, this is doing a lot better job of predicting our 3 data points. Still not doing a great job, right? But we can see we're getting a lot closer, okay? And so this is where we are on the contour plot, okay? After more iterations, okay, we now have an intercept of -0.23 and a slope of 3.63. So our slope is actually too steep compared to the true solution. We know the true solution has a slope of 3.1 and an intercept of kind of 1.8, okay? So right now our intercept is negative 2.3 and our slope is 3.6, okay? It's just a little bit too steep. And so and that's where we are over here, okay? The true solution is over here. So we can see, yeah, our slope is higher. It's up here, and the true slope should be down here at around 3.1, so we need to kind of bring it down. And our intercept is too low. Our intercept, the true solution is at 1.8, and the intercept. So you know, the shape of our contour plot kind of reveals that says there's, you know, a much steeper slope this way. And so urgently, what had to happen was the slope had to get a lot higher, and then once it got high enough, now we can start adjusting the slope back down, okay? And so this is after 100 iterations, okay? So it's traveling along this path right here a lot more slowly, okay? And so here it's saying, okay, we can make the slope of this line a little bit less steep, and to try to fit our data better, we're going to increase the value of the intercept. Okay, so the value of the intercept is now climbing towards the true solution of 1.8, and the slope is coming down towards the true solution of 3.1. So it used to be intercept negative 0.23, slope of 3.6, and after like a bunch of iterations, now the intercept is 0.62 and the slope is 3.4. And after, you know, a few hundred more iterations, our intercept is higher at 1.47 and the slope is 3.18. And you know, again, after maybe 1,000 iterations or so, it will kind of arrive at intercept 1.79995 and slope of 3.10001. Okay, a lot closer to the actual kind of solution there. Right? Does that kind of make sense? What's happening in these plots? That this one's showing the line that's trying to fit this data, and over here we're just trying to search for this. Okay, and again, this is it seems silly to do for linear regression, and I agree. It is silly to do for linear regression because in linear regression we know we can just type in LM and it's going to give us the answer, and we already know how to do this. Okay, but gradient descent is great for situations where we don't really know the answer, but I'm showing it here so you can kind of see how it's working on something that's familiar. And so when we jump to something like neural networks, then like you're not going to be able to like draw out this picture as well, but at a kind of fundamental abstract level, it's doing the same thing of trying to like pick out different weights and trying to fit the values, and it's trying to get the imaginary, there's not really a fitted line per se that we can draw, but it's trying to do the same thing. Okay, here's a picture of the gamma that is just a little bit too big, and you can see, you know, we started off here and we said downhill is in that direction, and we take a jump, a leap, and we end up on the other side, and so we end up kind of bouncing back and forth. All right, we still get to the bottom. Okay. Our leaps aren't so big that it breaks the algorithm, but yeah, we're kind of leaping a little bit too much. Okay, but if your gamma is way too big, so here, you know, I actually started at a different location, but you can see our leaps get bigger and bigger and bigger and bigger, and we are not going to converge with this with a gamma that's too big. Okay, let me give you your second view quiz answer, and the second view quiz answer is the letter B. B as in bear. B as in bear is your second view quiz answer, B. Okay, numeric gradient calculation and checking. This is kind of a way to check your own work, and it's a pretty good thing because one thing that I would say a fairly common issue in doing computational statistics, or basically anytime you're doing math related to the computer, is sometimes you do work and you're not sure if you did it correctly. Okay, so you like say, all right, I got to figure out the gradient, I got to figure out the derivative, and you come up, you get some, a bunch of letters, and you go, I think this is right, but you're not quite sure, right? And so, and you're like, well, and then I have to run this in code, and I hope this works. So there's a way for us to kind of like check our work, okay? And we can kind of check our work using numeric gradient calculation, okay? Numeric gradient calculation is not efficient, so you don't want to use this as a way of calculating your gradient iteratively, where you're gonna, if you had to do numeric gradient calculation and you're gonna do 1,000 iterations, this will really slow down your thing. But if you're gonna just do it once, it's quick and easy, and you can kind of say, all right, well, this is, we can check our answer, right? So I wrote, sometimes you found the gradient via calculus, but you're not 100% confident that you did it correctly. And so numeric gradient calculation is a simple but perhaps inefficient tool to find the gradient and verify this. And so I generally recommend always kind of finding the gradient analytically via calculus, and then comparing your analytic solution to a numeric gradient check. And if it does, then go ahead and implement the analytic solution. All right, and the way numeric gradient checking works is it's based on our classical definition of the derivative, where you have a function at x, and then you add a tiny little h, and then you say how much did the function change, and you divide by h, okay? And so we're just gonna do that numerically, okay? So when you have a gradient, okay, you have a vector of partial derivatives. And so this is the important thing, is that you have to do each component separately. You can't do numeric gradient checking of both values at the same time, okay? So here we have the gradient, and we have the partial with respect to x1, and we have the partial with respect to x2. And we have to do these separately. First, if we find the numeric estimate for the partial with respect to x1, and we find the numeric estimate for the partial with respect to x2. So the way this is going to work is you find the value of the function at your current location of x1 and x2, and you add a tiny little h just to the x1 component. You leave x2 the same. Okay? And you say, how much did my function change when I added a tiny little h to x1? And then you take that difference and you divide by h. You do the same thing for x2. You say, all right, here's my function at x1 and x2. I'm going to add a tiny little h to just x2. We leave x1 the same. How much did my function change when I added a tiny little h to x2? And then we divide that change by h. So let me do an example here. So we're gonna use the same kind of arbitrary function from earlier. And so remember, let me go way back here. We started off here, all right? So here's our function, okay? And we said the gradient at -5, 4 is going to be -14, 22.5. So this is the work that we did earlier today, okay? So this was the gradient, and we did this analytically. Okay, so now we want to do this numerically. So we start off with the function, and we say, all right, I'm going to plug in my current location, -5, 4. I plug that into the function, so I do, x1 is -5, so I do x1 squared, -5 squared, minus 2x1, so that's a plus 10, minus 0.5 x1, x2, so that is, -0.5, -5 times 4 is plus 10, and then plus 2.5 x squared, and 2.5 times 16 is 40. And so the value of the function right now at -5, 4 is 85. And so on the next step, what I'm going to do is I'm going to add a tiny little h, okay, first to the first component. So our x1 is -5. I'm going to add a tiny little h of 0.01. 0.01 is considerably large. Normally we would probably add something like 10 to the -5, okay, or something. You don't want to go too small because then again you run into machine epsilon problems. Okay, but probably something on the order of 10 to the 5 times smaller than whatever your current value is, right? So if your current value is 1,000,000, you'd probably add like 1, okay, 1 or 10. But if your current value is something like 1, you'd probably add 10 to the -5 or 10 to the -6. Okay, but anyway, here I'm going to just add a 0.01. Okay, so I know the function at -5, 4 is currently 85, and I say, okay, how much is the function at the location -4.99, 4? Okay, if x1 is -4.99 rather than -5. Okay, and so if you compute out this function at this location, you get 84.8601. Okay, so this changed. This became smaller by -0.1399, and if I divide by the size of h, which is 0.01, my estimate of the gradient, or at least the first element of the gradient, is -13.99. Okay, I do the same thing, but now for x2. So I leave x1 the same at -5. Okay, but here I'm going to change x2 from 4 to 4.01, and I say, okay, the function at -5, 4 is 85. What is the value of the function at -5, 4.01? All right, so I plug that in and I get 85.225. Okay, so how much did it change? It changed by 22.525. I divide by 0.01 and I get 22.525. The analytic results, when we did it, back on slide 10, the analytic results were -14, 22.5. My numeric estimate that I get just by adding kind of 0.01 to these things is -13.99 and 22.525, which I would say is pretty close to the analytic answers of -14 and 22.5. So this would kind of bolster my confidence and say my analytic results for calculating the gradient are correct. Okay, and so that's how we would calculate or estimate the gradient numerically there. Okay, we are going to set this gradient descent stuff aside, and we will come back to it, I guess, on Wednesday when we start doing, I don't know, maybe Wednesday or I guess Monday. Oh, I guess, man, the summer is like so fast. So second week Wednesday, we'll introduce neural networks and stuff, and then I got to talk about in third week Wednesday you have your midterm exam. So it's like, oh my gosh, that's already that's around the corner already. So I know we just started a week ago. So anyway, looking ahead to that. I want to, while we are talking about linear regression stuff, I want to bring up this topic of regularization. Regularization is another kind of tool that we have to help us avoid problems of overfitting. Okay, so overfitting is the idea that here's your data, your training data, and your training data has random noise, right? It reflects a bit of the true relationships in the population, the true relationship that exists in the world, but it also contains random noise. And in overfitting, it means you're starting to try to model and predict that random noise. That random noise is now part of the model. And so when you get new data that has different random noise, the model that you trained doesn't perform as well. Okay? We covered cross-validation as one way to try to help us avoid overfitting. Cross-validation says, okay, don't use all of your training data, split it apart into a training and testing set, and then train on this part and test it out on the testing side, and you can see how well you're performing, and by kind of using that, you can try to pick out a model that performs well on both the training and testing, and not just the training only. Okay. Regularization is a different strategy to avoid overfitting. And the way it avoids overfitting is it modifies the loss function by penalizing models that are a little too complex, right? So right now our loss function just says minimize the sum of squared residuals, or the mean squared error. And here we're going to say, yes, we want to minimize the sum of squared residuals, but we also want to make sure we're not getting too complex of a model. Okay, so it's kind of like adding this second priority, right? So it's kind of like, somebody says, I want you to throw the best party ever, okay? And you go, all right, what's important? What's going to make the best party ever? And you say, okay, well, we're going to get, we're going to rent this mansion, and we're going to get like live entertainment and things like that. And they go, oh, wait. We don't have that much money, right? We gotta, this is your budget. So I want you to throw the best party ever with a budget of $200. And you're like, oh, okay, now we're gonna have to do it in, my backyard or something, right? So it's kind of like that. We want to fit our data. We want to shrink our mean squared error as much as possible, but we're also kind of putting in this a little bit of a restriction here by saying, okay, you're not allowed to have a super complicated model, okay? So right now, before we do regularization, this is our loss function. We're saying mean squared error, we want to shrink this, okay? And if we say, what we want to do is we want a model that minimizes the mean squared error, what could end up happening is we end up picking a model that's overly complicated. So, when you took 101A, if you took 101A or you did linear regression, I don't think they covered regularization, but what they said, what they should have said is like, don't use R squared as the only measure of how good your model is. Because if you use R squared only, you can always edge out a little bit a higher R squared value by continuing to add more and more and more variables, okay? And so you had ways to kind of evaluate this, and you would say, all right, let's look at the summary table and see if the coefficients are significantly different from 0. Or we'll evaluate our model using like AIC and BIC, and these are performance metrics that also include penalties for complexity, okay? That's our best, penalties for every kind of predictor term here, okay? So again, if we say the only goal is to shrink mean squared error, that's basically saying we just want to maximize our R squared value, okay? What we want to do is we're going to modify the loss function. And so I wrote, you've seen the effect of modifying the loss function in your homework, right? So right now you're doing what happens when you have weighted least squares. And what you see is that when you adjust the weights, regular ordinary least square says we're going to try to shrink the residuals on all of our data, okay? We want to minimize the sum of squared residuals on all of our data. When weighted least squares, we're saying some data is more important than other data. We're saying these values are like more important, and we really want to minimize the residuals on these values. And these values are not important, and I don't care if they have big residuals, is basically what we're saying when we do weighted least squares. So you can adjust it. So I think you have data that looks like this, and so your regular or ordinary least squares line looks something like that, okay? If you say these are the important ones, okay? These 2 points here are really important, and I don't care if we have huge residuals on these points, then the fitted line ends up looking like this, right? Because we're saying, I want really tiny residuals here, I don't care if I have a huge residual here and here, okay? Or if you say these are the important ones, this one over here and this one's really big, and I don't care if I have residuals over here, then you end up getting a line like that, right? So we're just saying, like, with weighted least squares, we're saying these points are more important, and it's more important that I shrink these residuals, and I don't mind if I don't shrink these other residuals. And it's almost like at a certain point, if you weight these points like by a million, or something close to infinity or whatever, and these ones go down to 0, it's basically like throwing those data points away, okay? With weighted least squares, it's kind of like if you weight certain values to have values close to 0, you're basically, or if you weight them to 0, you're basically throwing those data points out, and you're saying, oh, don't even bother fitting those data points. So that's what weighted least squares does, and changing that loss function dramatically changes what your slope and intercept will be, right? You end up having end up having a negative slope, despite having the same data. By changing what the loss function looks like, you end up getting a very different slope and intercept. Okay. So what we're going to do here is we're going to say the objective function that we are trying to minimize says, okay, we want to shrink the loss function. We want to shrink mean squared error. We want that as small as possible, but there's a penalty for models that get more complicated, okay? If the model is really complicated, you might be shrinking the loss function, but this complexity penalty is going to get bigger and bigger and bigger, right? It's, I want to maximize my fun. Okay, that's great. Maximizing your fun might also be like cost money. And so depending on how resistant you are to spending money, right? You might say, all right, let's do this thing, and it's going to cost a few $100s, and I don't mind, okay? Because I'm having more fun. Or somebody could say like, okay, well, so depending on kind of the penalty for whatever it is we're doing here, we're going to end up picking something else. Okay. Now, one thing about the notation is this is L prime. This is I'm just using a textbook's notation. This is the loss function plus the penalty term. It is not. I know in other classes, when you have the prime, it's like the derivative. Okay, this is not the derivative of the loss function. It is the loss function plus the complexity. It is the modified loss function. It is not derivative of this, okay? This is just I'm just following the textbook notation where we call this modified loss function L prime. Okay, here's my other analog to real life, okay? So maybe you're searching for a place to live and you're considering apartments, and I don't know how much apartments cost, but let's say one apartment is like $2,400 a month, and it's close to work. So you have a 10-minute walk, okay, or 10-minute commute to work. So that's nice, okay. And then the other apartment is cheaper, $2,000 a month, but you got to commute 40 minutes each way, okay. And so depending on the person, you might say, all right, well, what's important to me is saving money, okay, and I'm willing to drive, okay, and I'd go with the cheaper apartment, okay, and the other one might say, no, you know what, I hate commuting, and I don't want to lose, basically an extra hour of my life every day, and it's worth to me paying the extra thing, right? If money is the only factor that matters, then you always just pick the cheaper apartment, okay, but if your time is also very important, then you might pick the more expensive one, okay? And so I said, depending on the person, you have this preference factor, right? If you value your time greatly, okay, like you have an active social life outside of work, or you just really hate commuting, then you'll weight the penalty of having the longer commute much heavier. and you'd probably end up selecting apartments that are closer to work, okay? On the other hand, if you don't mind commuting, okay, and you enjoy, I don't know, listening to podcasts or audiobooks or whatever, you don't need a ton of time outside of that, then you'll say, oh yeah, you know what, the money is better, and so, you know, you'd probably pick the apartment with the lower rent, okay? We are not, at the end of the day, we're not going to kind of compare one model with another. Is we are modifying the loss function as a way for us to pick the optimal parameters, okay? We're still optimizing kind of the loss function. But the loss function is not just mean squared error. It factors in this, this penalty term, okay? All right, let me give you your third view quiz answer. Third answer is the letter A. A as in apple. A as in apple. Okay, so more generally, so here I've been writing lambda times complexity, but more generally we might write lambda times R of F. R is kind of your regularization function, your regularization term, and there are ways to measure model complexity, and you can read the Wikipedia article on regularized least squares. And so here you can see you have lambda times RF and things like that. So that's what we have here, lambda times R on the function. But let's go ahead and take a look, okay? So one way to measure a model's complexity is to count how many non-zero coefficients we have. So let's say we have two models. We have model A. Model A is going to fit a fourth order polynomial, and model B has a fifth order polynomial. So we know the fifth order polynomial is more complicated than the fourth order polynomial. The fifth order polynomial is, oh, I have these letters mixed up, sorry. Fifth order polynomial is w0 plus w1x and w2x squared and w3x cubed and w4x to the fourth and w5x to the fifth. And really, the fourth order polynomial is just a special case of the fifth order polynomial where we force the weight on the fifth order term to be 0, right? So if I say w5 is equal to 0, then it reduces down to a fourth order polynomial, and we know that this is a simpler model than this one, okay? So we can say, well, one way to measure model complexity is to count how many non-zero coefficients we have, okay? And the count of how many values are non-zero is technically known as the L0 norm of a vector. So if we gathered all of the coefficients together in some vector W, okay, we could say, all right, what is the L0 norm of the vector, which will just be a count of how many values in that vector are non-zero, okay? And we can say, okay, well, our loss function is our mean squared error plus lambda times the L0 norm of W. One thing is that it is really difficult to optimize the L0 norm. The loss function, we would say, is not convex, and you technically have to consider all possible permutations of which elements in W are non-zero. And then once you say, all right, these are the elements that are non-zero, you have to go and figure out what those weights should be, okay? And if you have more than just a few terms, so maybe if you have like 3 W terms, it's not that hard. But if you have like 20 of these things, now you have 2 to the 20 possible permutations of which W terms are non-zero, okay? 0 or non-zero, right? So I mean, with 10 terms, you have like 1,024 ways to have, some W's non-zero and some W's 0. And the computations become staggering. So we generally don't try to optimize this thing. So I think this is L0 penalization. So you can do lambda times the L0 norm here, okay? So I don't know if can you guys see this? This is sometimes when you read things on Wikipedia, the notation gets a little bit scary. But this is basically just mean squared error here, right? You do y minus xw, and you're taking that difference squared, and the norm 2 squared is basically the sum squared error, so 1 over n, and then here's your lambda times the w0. W with the L0 norm, okay? But here again it says it's very difficult to do, okay? So we generally don't use the L0 norm, okay? Instead, we might do something called the lasso, okay? Lasso uses the L1 norm, okay? The L1 norm sums the absolute values of the terms in our W vector. Okay, so instead of counting which elements are non-zero, we can take the absolute values of each of these values, and then we'll serve this, all right? And that serves as a measure of complexity in the model. So non-zero values will contribute to the penalty factor. Larger values and larger coefficients will contribute more to the penalty. And if a coefficient is 0, then that variable basically isn't counted, is not part of the model, and it's not counted towards the penalty factor. So when we try to optimize this loss function, anytime we say we're gonna, we're trying to shrink the mean squared error, okay, we might say, okay, we can shrink the mean squared error a little bit more by changing the weight of this term from 0 to, I don't know, 1 or something like that, okay? And if we do that, then however much our mean squared error shrinks has to be more than basically lambda times what that W term grew by. Okay. Another way is we could use the L2 norm, the sum of the squared elements in W. This is known as ridge regression. So we can do the L2 norm, which is basically the Euclidean length of this W vector, okay? Or I guess the squared Euclidean length of this W vector. So you take the elements of W, you square them, and then you add them up, multiply that by lambda. And what this will do is, because you're squaring values, big values of W are penalized more heavily. Small values of W are penalized less, okay? And that's known as ridge regression. One effect is that ridge regression favors or prefers values in W that end up kind of more similar to each other than having like one value of W that's like really big, okay? Students, and when I was first learning this, I too kind of had this concern that said, why are we using the size of the coefficients rather than just how many coefficients? Like when we use the L0 norm, like that makes sense. If we have a bunch of terms that are non-zero, that's a more complicated model, and terms that are 0 is a less complicated model, okay? But here we're saying like, okay, we're gonna use the size of the coefficients themselves, and that feels like if I have two models, and one model has 3 non-zero terms and another has 3 non-zero terms, but this model has bigger coefficients than the other model, we're going to say the one with bigger coefficients is more complicated than the other model. And that was uncomfortable to me, because I was like, both of these things have 3 coefficients. Why are we going to say the one... I ran out of battery. Why are we going to say the one with bigger coefficients is more complicated than the model with smaller coefficients? I hope I got battery charge on here. No? Sorry, let me pause. Okay, so I had all these concerns. I was like, if these two models have the same number of terms, I felt like they should be equally complex, and that the one with just bigger coefficients shouldn't be the one that's counted as more complicated. But that's what we're kind of saying over here. We're saying like bigger coefficients, more complexity, heavier penalty. Okay, and then the other kind of concern I had was like, because if you think about what your coefficients are, those coefficients are heavily determined on what size unit you have, right? So if you measure someone's height in centimeters, and you say this person's 170 centimeters, and let's say we're predicting weight based on height or something like that, and you're saying, okay, every time someone's height goes up by 1 centimeter, we expect their weight to go up, I don't know, 0.01 kilograms. Okay, so your coefficient is 0.01, right? And then let's say somebody else did the same kind of thing, but they measured in meters, right? And so now we're saying, the person's height is like 1.7 meters, okay? And so now to say if somebody goes up 1 in x, they're going up an entire meter in height, which, we can't really do, okay? But then, so now you're, if we have this person, an increase of like 1 entire meter might be like, I don't know, 50 kilograms or something like that, right? So now your slope is much, much, much bigger, okay? Depending on the unit, okay? And that doesn't make sense, that just because we use different units, now we're going to have different coefficients, and now we're going to have different complexity values, okay? Because complexity is based on the size of the coefficient itself. So if the slope is 0.01, that's less complicated, and if the slope is 50, we're saying that's a more complicated model, and that doesn't make sense, right? So let me try to address both of these concerns, okay? So one is anytime you're going to do lasso or ridge regression or something, okay, you want to standardize your values, okay? So you want to kind of turn everything into, say, z-scores, all right? So that will get rid of the issue of having different units. Because if somebody is 1.7 meters tall and somebody's 170 centimeters tall, if you turn them into z-scores, they're going to have the same z-score, okay? It's not, so you want to kind of standardize things. So basically, subtract off the mean so that the mean is 0, divide by the standard deviation so that the standard deviation is 1, okay? So that would be standardizing your values. An alternative way to standardize would be to scale all of the values so that they go between 0 and 1. And that would be something if like you can't have negative values or something like that, okay? So standardizing the variables address kind of the concern of different units. And so that's one thing that's important, okay? All right, but still the other part, which is like, okay, why would bigger coefficients still mean more complexity? Okay, and so here's kind of like this little thought experiment that I kind of want us to kind of talk to. Let's say we have two competing models. They both use the same input matrix X, and that matrix X has been centered and standardized. Both of models have 4 X variables, and both models have the same coefficient for X1, X2, and X3. Okay, and the only difference is that model A has a larger coefficient for X4. Let's say its weight for X4 is 1, and model B has a tiny coefficient for X4. Let's say its weight is 0.01. Okay, so with the exception of coefficient X4, model A and model B are the same. Okay, and I'm going to argue that model B, because it has a smaller coefficient than model A, is the less complicated model or less complex model than model A. Okay, because basically the tiny coefficient means that changes in that variable X4 have little impact on the outcome variable. Okay, so even if model B, if model B has its weight for x4 is 0.01, basically it's saying x4 is not as important of a variable. Okay, and so when x4 changes, model B is hardly affected at all. It doesn't actually really care. You can almost throw away that variable x4 and it barely has an impact on model B. Okay. Whereas model A, it still places an important kind of weight on that variable x4. Kind of an analogy is I say, let's say you have two students, and both of these students are involved in several clubs on campus. I don't know if this sounds like any of you. One student is like fully invested in all of their clubs, and they're in like leadership positions in all of these clubs, and I would say their life is busy and complicated, okay? The other student maybe is involved in the same exact clubs, okay? But this other student isn't in the leadership positions, isn't as committed to every single one of these clubs, and so when that student says, it's all right if I miss a meeting, it's not that big of a deal, okay? It's not that big of a deal. And I would say that student who's less committed has the simpler, less complex life, right? Because the amount of kind of weight and importance that they're putting on all of these different things is just a lot less, okay? And so similarly, we can kind of actually treat the size of the coefficient itself as a measure for kind of how important and how much emphasis it's putting on each of these variables. And if it's putting less emphasis on the variables, we're going to say it's less complicated, okay, with respect to that variable, okay? So the weight placed on each of these variables can actually be used as a measure for how kind of complex the model is. Does that kind of feel okay, that argument there? Okay. So what did I write? Okay. One thing is the intercept terms are not factored in to the lasso or ridge regression penalties. So I've been writing like you have lambda times the W, the L1 norm or the L2 norm of the W vector don't include the intercept term in that W vector. Okay, so only coefficients that are multiplied by the predictor X variable are included in the penalty term. Okay. So let me just kind of illustrate how this could kind of work, okay? So here I've got x1 and x2, and the true relationship between t and x1 and x2 is that we're going to do x1 times 1.5 and 0.5 times x2. And then we're just adding some random noise, and I'm going to fit a model, okay? In this model, I'm not going to fit an intercept. We're just going to estimate, based on the random data I've seen, we're going to estimate what is the slope for x1 or the weight for x1 and the weight for x2. And so based on my random data here, so it's based on the true model where I've added some random noise, it's estimating the slope or the weight for x1 is 1.46. And the weight for x2 is 0.45. And that's kind of close to the true values of 1.5 and 0.5, but not exactly so. Okay, the OLS loss is going to be, T minus XW transpose times T minus XW. That's going to be the sum of squared errors, all right? And here I write a function in Optim. I don't know if you guys used Optim. Maybe we'll have I might have some slides at the end on how to use Optim. But basically, I just said, okay, starting off with an arbitrary weight for x1 and x2 of 0 and 0, optimize this and figure out what is the values that will minimize the sum of squared errors, okay? And so Optim arrives and says, okay, the values that will minimize the sum of squared errors are 1.4588 and 0.4533. Okay, which matches up exactly with the LM function. So all to say is Optim is a way to kind of minimize whatever loss function. So right now my loss function is just the ordinary least squares loss, which is sum of squared errors here. and I can kind of plot this OLS function, and we get this thing. These are the coefficients for x1 and x2, and so for our data, the true value is pretty close to 1.5 and 0.5. Right, it's 1.458 and 0.4533. Right, so this is the values of the OLS loss function. Okay, what I'm going to do now is I'm going to write a function in R that says our L1 loss, okay, the lasso loss is going to be the OLS loss, okay, which is this function here, all right, which is this sum of squared errors. We're going to take that, okay, which is just this L, plus lambda times the W1 norm. So I'm going to take absolute values of W1 and W2 and sum them up. Okay, so that's this. And we can take in different values of lambda. All right, and so this is what we're going to want to do. We're going to try to minimize this using Optim. Okay. So one thing to note is if we only cared about minimizing this L1 norm here, then the contours of the loss function would basically be concentric diamonds centered at the origin, right? Because you think about what the L1 and L2 norm look like, or what the L1 norm looks like. So we can have different values of W1 and W2, and you know, if I have let's say I said the norm of W1 is equal to of W, the L1 norm of W is equal to 2. All right, what are the values you can have? Well, you can have W2 be 2 and W1 be 0. You can have W1 be 1 and W2 be 1, or you can have W1 be 2 and W1. I'm getting all tongue-tied here. But you can have basically 2, 0. Okay. You can have 1, negative 1, or 0, negative 2, right? And you can kind of trace out a diamond of this is where the L1 norm of W is equal to 2. Okay. And similarly, you know, you would get kind of these concentric diamonds, or if you said the norm is equal to 1. So that would be if we were trying to like optimize just W1 and W2 only, okay? But that's not the function we're trying to minimize, right? We're trying to minimize this and the OLS loss function. So the OLS loss function looks like this. So what we end up getting is kind of a hybrid of these two things. So let me just show you what these are the results. So the OLS values is 1.458 and 0.4533. Okay, and as I try to optimize this, I can change my lambdas, and we can see as lambda gets bigger, these values shrink. So it goes from 0.458 to 1.436 to 1.345 to 1.23. As my lambda gets bigger and bigger, as lambda keeps getting bigger, we get 1.049, 0.595, until we effectively get zeros here, okay? And that's with the lambda that's really big. This is a plot. So here, this is the original OLS loss function, and this red dot represents, you know, the slope for x1 and x2, or the weights for x1 and x2 that minimize that function, 1.458 and 0.453, okay? And this is the contour of the lasso loss function, which is a combination of the OLS loss plus the L1 norm. So So imagine the OLS loss function looks like this, okay? And we're kind of like getting a hybrid of basically this and this together, right? So I got these diamonds together here. I don't know if it's that. So we have these two things kind of going together, and so you'll kind of see it a little bit. So in the beginning, it looks, the lambdas are small, so there's a lot more emphasis on this, okay? As I increase the lambdas, we're going to put more emphasis on this side, and we're going to get kind of a blend here, okay? So here it is, as the lambda is getting bigger, so you can start seeing these little kind of sharp corners start to form when it encounters basically the x-axis, x1 axis or x2 axis, okay? And so as lambda gets bigger, it becomes more like diamond shaped, okay? Until, you know, we get to a point where lambda is really big and it looks more like the diamond side. It looks, again, it's still including the OLS thing, but so it starts off something looking a lot like OLS, and as we increase the importance of the diamonds, you know, our contour plot reflects that. This blue dot represents what is kind of the solution for what is the weight for x1 and x2. And so in the beginning, when our lambda, the penalty for complexity is quite small, the solution is very similar to the OLS solution, okay? And in fact, with lambda is equal to 0, it's just the OLS solution, okay? As lambda gets bigger, what we see is that the coefficients W1 and W2 get penalized, and so they shrink, okay? So if we say lambda is you know, at this value, the OLS solution that minimizes the sum of squared residuals is here. This solution doesn't minimize the sum of squared residuals. It gives something a little bit different, but it minimizes the total between the sum of squared residuals and the complexity penalty. And it minimizes it by saying, okay, don't pick the big W1 and don't pick the big W2. We're going to shrink those a little bit. Okay, and as we increase the penalty for having big W1s and W2s, we say, okay, W1 and W2 have to be even smaller, right? It's kind of like somebody says, okay, you were planning the greatest party ever, but now your budget is 200 bucks. Now your budget is 150 bucks. Now your budget's 100 bucks. And you have to keep kind of cutting things and shrinking them, right? You say, okay, instead of buying 8 pizzas, we're going to buy 7 pizzas. And now we're going to only buy 6 pizzas and this much soda or something like that, right? And you're starting to shrink these things until at one point you're like, okay, no more pizzas, only soda, right? And then your budget keeps shrinking. And then, so now you're like, okay, you gave me no budget, and now I can't buy anything, right? And so now my coefficients are 0 for both of these things because we've penalized the W1s and W2s so much that we're just like, okay, everything's just got to be 0, right? I can't do anything here, okay? So that's what happens. And you can kind of see this, the path that this takes is it kind of goes down a diagonal line towards the axis, and then once it hits the axis, it can't shrink W2 anymore, right? W2 is at 0, so that can't shrink anymore. So now only W1 will shrink, okay? And I've kind of written that out. L2, the L2 norm, instead of diamonds here, what does the L2 contours look like? L2 norm contours, right? So you're doing the sum of squared values. Okay, if you're adding the sum of squares, if you're doing like basically W1 squared and plus W2 squared, you're going to get circles, right? X squared plus y squared equals some constant, or basically your radius squared. Okay, so you're going to get concentric circles here. And so you're going to see something similar, but also a little bit different, okay? So here, we start off over here 1.458 and 0.453. And as we do the lambdas, notice what happens. These shrink from 1.45 down to 1.25 to 0.92 to 0.74. But these ones actually go from 0.45 to 0.579, it gets bigger, to 0.635. This one actually gets bigger, and then it starts coming back down to 0.573. Okay. And then, you know, as the lambdas get bigger, they keep shrinking. So we start off, again, looking more like this, but as I increase my lambdas, it's going to start shifting more towards this, okay? So what we see is that the optimal solution, very close to the red, which is the OLS solution, but as I increase my lambdas, notice my blue dot is climbing actually upwards, okay? And it's climbing towards this line, y equals x, okay? And then once it gets to a point, it starts moving towards the origin, and we get something that looks a lot like concentric circles. But again, it's a blend between the OLS contours and these concentric circle contours, okay? So going back, shrinking the lambda, what do we see? It climbs up, and then it starts moving towards this, okay? And that's with lambda equal to 1,000, all right? And so what's going on is that if you think about the sum of squared things, right? So if we're doing a W2 norm squared, and we have W1 squared and W2 squared is kind of our penalty term, what happens is if this is really big, if this is a big value, okay, and you square it, it's like this big thing, okay? And whereas if this is small and you square it, you get this really small thing, okay? And so just like squared residuals hate having any one outlier that's really big, the ridge regression penalty, the W2 penalty, hates any one coefficient that's too big, okay? And so what it will try to do is it will actually try to make the two coefficients more similar in size, okay? And that's what this kind of dotted line here represents. Is this is where the W1 and W2 terms are the same size. So it actually pushes the dot towards this location where W1 and W2 are the same size, and as it gets closer to that, then it starts to shrink both of them equally, okay? But until then, it's actually going to nudge one of them to be bigger as it's shrinking the other one, okay? So the larger coefficient W1, actually not the intercept, just the x1 term, sorry, should just be the x1 term is penalized more heavily than the smaller coefficient, and it causes kind of the OLS function to grow, and we can reduce the W2 coefficient, right? So again, when you square things, shrinking something from 11 to 10 shrinks it a lot, right? 121 to 100. 11 squared is 121, 10 squared is 100. Whereas shrinking from, say, 3 to 2 shrinks it only a little bit, going, 3 squared is 9, 2 squared is 4. So going from 11 down to 10 shrinks by 21, whereas shrinking from 3 to 2 only shrinks by 5. So it's going to kind of shrink the larger coefficients a lot faster. Okay? Another way to think about this regularization stuff, okay, is you can say, all right, here for ridge regression, we have residual sum of squares, basically our OLS loss function, plus lambda times the sum of our betas squared, okay? For here, we have ridge, ordinary least squares regression, residual sum of squares, plus lambda times the absolute values of the beta, okay? You can think of this also, this is in the form of having a Lagrange multiplier, right? So when you use a Lagrange multiplier, you have a function that you're trying to minimize subject to a constraint, right? Here the constraint is, and you do lambda times this or something, okay? And so now it's kind of like the constraint is that the sum of beta squareds is less than some unknown, some constant s. Okay. Over here, this is in the form of that the constraint is that the sum of your absolute values of beta is less than or equal to some constant. So you can think of what we've been doing. The loss function plus some penalty. You can think of that. This is in the same form of having a Lagrange multiplier, which is what we use when we're trying to minimize a function subject to a constraint. Okay. And so if you think of it that way, the constraint for lasso is basically you have these concentric diamonds. For ridge, the constraint is basically your beta terms have to kind of fit this, have these circles here. Okay, so this is a diagram that comes from our textbook. Just kind of copied that. And again, this is the beta hat that corresponds to ordinary least squares regression. You have these kind of contour lines that and you have some kind of constraint, right? So you have some kind of constraint, and this is the solution is going to be where the OLS touches the boundaries of the constraint as well. All right, let's see. How many view quiz answers have I given you? 3? Okay, go ahead and give you the fourth one. The fourth one is the letter D. D as in dog. D as in dog. All right, regularization and the variance of parameter estimates. So we said regularization helps reduce overfitting, and it also helps us shrink the variance of our parameter estimates. So what do we mean by the variance of our parameter estimates? It's the idea that there is some true relationship, but because whenever we gather data, it is a random sample with noise around the true relationship. So I might gather data and I might fit a line, okay? And you might gather data from the same population, but your random data is different from my random data. And so when you fit your model, we can both use like the same kind of model. Your parameter estimates are different from my parameter estimates, right? So if I say the slope and intercept is this, you can gather different data and you end up with a different slope and different intercept based on what random selection of data that you have. So we're saying our parameter estimates of what the slope and intercept or whatever our weight values are have variance, okay? And it's undesirable, like if my parameter estimates and your parameter estimates are similar to each other, we would feel good. We'd say, okay, we are both on the right track. But if my parameter estimates are wildly different from your parameter estimates, that makes us uncomfortable. It feels like either I did something wrong, or you did something wrong, or something's wrong with our data. It doesn't feel good if your results are wildly different from my results. Okay, so we don't want huge variation in our parameter estimates. Okay, so I'm going to show you a bunch of pictures here. Okay, but basically, I'm going to show you, you're going to see a cloud of points, okay? This is, the original data, the true relationship has, the coefficient is 1.5 and 0.5, okay? The true relationship has W1 equal to 1.5 and W2 equal to 0.5. And I think when we did it, we got like 1.458 and 0.45 or something, right? That was one of our values here. Here, I just ran the same thing 1,000 times. I said, let's generate random data and fit ordinary least squares regression. And when we do that, sometimes I got values as high as W1 has a slope of 2.0 and W2 has a slope of 0.2. I got values as low as W1 has a coefficient of 1.0 and W2 has a coefficient of 1.0 or something, right? So this is just a cloud of different W1 and W2 values I could get based on just the random data set that I generated, okay? We know the true values around here, but again, because of randomness, sometimes my coefficient estimates are up here, sometimes my coefficient estimates are down here, sometimes my coefficient estimates are over here, okay? What are the coefficient estimates if I put in lambda equal to 10, okay? with lambda equal to 10, we're penalizing these things, and basically this entire cloud in black gets shifted a little bit down diagonally, and you can kind of just, like, the red cloud and the black cloud are actually like the same shape, it's just like it's been shifted, okay? Here I have applied a bigger lambda penalty, and so this cloud just gets shifted even more. It's the exact same. Like, you can see these 3 dots here kind of forming a pattern. Those 3 dots form the same pattern. It's the exact same cloud just getting shifted. But what's happening is that when this cloud crashes into the x-axis, they just get zeroed out, okay? So this entire thing gets shifted down, but these points that kind of crash into, not the x-axis, I guess the, what is this, the W1 axis, okay? They just get zeroed out because it doesn't make sense to have them be negative because that's going to actually add to the penalty here, okay? But this exact cloud kind of, you can see like this pattern here and that pattern there, kind of, it's just kind of shifting. And so as I increase the lambda penalty, what it's doing is it's just kind of like crashing the thing diagonally, and these things just zero out, okay? And so actually when they zero out, that is a way of like reducing the variance here by just kind of zeroing them out. And in fact, if you maximize your lambda entirely, you can't even see it, but there's like a blue dot. Basically everything has turned into 0, okay? Now this is like too extreme where we have such a big penalty that, you know, our best interpretation is to say, okay, everything, just turn everything into 0. So yeah, maybe not the greatest, but it is an effective tool, and it can be used as a way for variable selection. You can say, all right, if we keep kind of shrinking these coefficients, these ones become 0, and we can just say, all right, I only need these variables here, right? So here there's only 2 variables, W1 or X1 and X2. But you might have a thing where you have like 17 X variables, and after applying some lambdas, after applying lasso regression, maybe it reduces it down to 12 variables, and you can eliminate 5 of them because it said, you know, these coefficients are small enough to 0 that with a little extra lambda penalty, they zero out, okay? If we do the same kind of thing with ridge regression, the cloud, you can kind of think of the cloud being on, I don't know, a rubber sheet, and that rubber sheet is going to get squished towards this axis of y equal, W1 equal to W2, right? And so now this entire cloud has gotten like squished down, okay, into this shape over here. And as you kind of go even further, right, these things shrink down, and you can even see like little weird patterns, right? So if you look at the black dots, you have these dots right here. This form, they're also still right there, and they're also still right there. And they're also kind of still right there. So you can kind of see like little weird things that pop out in the original data, like still exist in these clouds as they're shrinking down. It's like they're still reflecting kind of the oddities that happened, right? So these kind of 4 dots here and those 4 dots, they're all the same 4 dots corresponding to the same kind of random data sets. But again, the parameter estimates just look different based on the penalties that we've applied. Okay, we'll take a look at this a little bit more using something like GLMNet to kind of estimate these things. But yeah, that is it for today's lecture on regularization. So we'll end here. Have a great rest of your day, and we will see you on Wednesday.